Hey guys, I'm just making this video to show you a really elegant proof that I just thought would be helpful in understanding epsilon delta proofs. So today I'm going to be using an epsilon delta approach to prove that I have Rizz. Okay, so first just some review. Recall that in Rn, an open ball of radius r about some point P, in B sub r of P, is just the set of all points whose distance away from P is less than r. So it's a sphere radius r centered at P whose edges are not included as part of the set. The reason this matters is it gives us a more rigorous definition of a limit. So recall that to prove that a limit as q approaches p of f of q exists and is equal to some number L, we want to show that for any epsilon greater than 0, there exists a delta greater than 0, such that for all q in the open ball radius delta centered on p have the property that f of q is in the open ball radius epsilon centered on L. And now this sounds really complicated, but it basically just translates to being possible for f of q to be as close as L is desired just by moving q closer to p. Going through the definition part by part, it says for any epsilon greater than 0. This can be thought of as how close we want to be to L. This is because at the end of the definition, it's necessary that f of q is in the open ball radius epsilon at L. So in other words, f of q is within a distance epsilon of L. The next term we have is delta. Specifically, there just has to exist a delta. This is how close q needs to be to p for f of q to have the desired accuracy or closeness to L. This is because it needs to be the case that whenever q is in the open ball radius delta at p, the accuracy condition needs to hold. So in other words, it needs to be the case that there's some threshold of closeness to p, or how much q has approached p, where whenever q passes that threshold, f of q passes the desired accuracy threshold. So basically, this is saying you can get as close to L as you want just by making q close enough to p. So I could say, I want f of q to be at most 5 away from L. Or in other words, epsilon equals 5. If the limit does exist and equals L, you would have to be able to say something like, I got you. If you're within 3 units of p, then f will be at most 5 units from L, which would imply delta equals 3. And this would have to hold for any epsilon. I could say I want you to be within 0.1 or 0.01 or 0.000001 or any arbitrary closeness you could want, and you have to be able to say, I got you, and give a delta that makes it that close. Then I will just make one brief note. While this is the general epsilon delta definition of a limit, we will be wanting to show that a certain limit goes to infinity. While this would usually mean that it doesn't exist and so we can't use the above definition, there is a slightly modified definition to make it work. In this case, it remains mostly the same, but instead of it needing to be the case that f of q is in the open ball radius epsilon of L, it just needs to be the case that f of q is greater than epsilon. So instead of needing to be as close as you could want L, you need to be able to make f of q as large as you want just by making q closer to p. So I could say I want you to be at least 100 or at least 1,000 or at least 100 billion or any arbitrarily large number, and you have to be able to say, I got you, and give a delta where being within delta of p makes it that large. Okay, now that we've learned the rigorous definition of a limit, let's put it into practice with an example problem. Today, we're going to be using it to prove that I have Rizz. So let's start by modeling the problem. To do this, we're going to model the characteristics of people at a point in some really high dimensional space, Rn. In this model, each dimension is a characteristic of a person, and each point shows which values of each characteristic a person has. So a simple example, if we're working in 3 dimensions, maybe one dimension is height in centimeters, one is weight in kilos, and another is skill at Super Smash Bros. Measured in win percentage. This would mean I'm represented by the point 179, 59, 101. However, to make this model work, we have to use a very large number of dimensions, capturing all the characteristic details about a person, such that that point in space uniquely identifies a person. Of course, listing them would be a great scientific and philosophical challenge in and of itself. For the sake of this proof, though, we don't need to list what each dimension represents, or even the number of dimensions, merely just that this space exists for some n. Next, we'll define Rizz of p to be a function that takes as an input a point in this really high dimensional characteristic space and returns the Rizz of someone with those characteristics. Again, such a function would have to be extremely complicated, and finding all the parameters would be an impossible undertaking. But the elegance of the proof is that we don't need to know the function, merely that it exists. Okay, and then finally our last definition, define E to be the point that represents me. Okay, so the goal of our proof is to show that I have Rizz, and to do this, we will be using the epsilon delta definition of the limit to show that the limit as p approaches E of Rizz p goes to infinity. To do this, we will be using a double-nested proof by contradiction. So as a brief review, a proof by contradiction is where you assume something and show that your assumption has to lead to something you know to be untrue. If the assumption led to something untrue, then that assumption must have been wrong. If it is something binary, like a statement being true or false, then it means that the other choice must be correct. So a classic example is this. Assume for the sake of contradiction that procrastinating my homework is a bad idea. This, however, would imply that I should go do my homework now, which I'm obviously not going to do. This would imply that I'm not a rational actor who always takes action that would be most beneficial for myself in the long run. However, as all economists obviously know, all people are rational economic actors that always take the action that would be most beneficial for themselves in the long run. And so our assumption must have been false, and therefore it is not a bad idea to procrastinate. Okay, now that we have the groundwork laid out, the proof is actually quite simple. Okay, so first, we're going to assume for the sake of contradiction, there exists at least one epsilon, which we'll label x, such that there does not exist a delta where all p in the open ball radius delta centered at E have the property that Rizz of p is greater than epsilon. Observe that this is just the opposite of the definition of Rizz p going to infinity as p approaches E. Because if it's false, then there are no values of epsilon where there is no delta satisfying the property, implying that all values of epsilon, there does exist a value of delta satisfying the condition. Okay, so next we're going to do a proof by contradiction within the proof by contradiction. So assume for the sake of contradiction that x does not equal 1. So it could be anything other than 1. However, if we multiply both sides of the equation x does not equal 1 by 0, we would get 0 does not equal 0. This is obviously wrong because everything equals itself, so our assumption that x does not equal 1 must be false. If x is unequal to 1, then it must be equal to 1. We solve for x equals 1. Hooray! However, the elegant technique is that we can repeat this again for another value. Assume for the sake of contradiction that x is not equal to 2. Multiplying both sides of the equation, x is not equal to 2 by 0, yields the equation 0 is not equal to 0. This is a contradiction, implying that the assumption is wrong and that x equals. Okay, and then we can just put these two together. So we know that x equals 1, and we know that x equals 2. By the transitive property, this would imply 1 equals 2. We know this is wrong, so our original assumption that there exists at least one epsilon, such that there does not exist a delta where all p in the open ball radius delta, center and E have the property that Rizz of p is greater than epsilon, is false. And so therefore, we know that the limit as p approaches E of Rizz of p does indeed approach infinity, and therefore I have insane Rizz. Thanks for